All right, let's look at section 5.7, logarithmic differentiation. So these are when you're working with integrals that wind up in their answer having natural log. All right, so there were a couple of problems on the test that required it. And what makes it necessary is if you had a problem like this one, number 15, and you tried to do it using a power rule, which is what we normally would have done, you might have tried to rewrite it so that that denominator was up on top, no denominator, using a negative exponent, right? Then you might think, okay, so I'm going to take that 3x to the third plus 7. I'm going to add 1 to this exponent here, but you would get a 0. And you know how the power rule says you should divide by that new exponent. So you'd have that division by 0 happening. So when that happens, that's the time when you really need to use logarithms. Use this logarithmic differentiation. Because you know that when you take the derivative of natural log, it turns out to equal 1 over x. So if you do the reverse of that, if you try to integrate 1 over x dx, you're going to wind up getting the natural log, and it does have that absolute value on it. Okay, but that's the idea. Okay, and when you know that this is what's going to need to be done, is when that denominator is just to the first power, like it is here. Okay. All right, so I'm going to go ahead and work the problem then. So I'm going to choose u to be 3x to the third plus 7. So you'll see why this is nice having that x squared up there, because du would be 9x squared dx. The derivative of 7, remember, is going to be 0. All right, so up here on top, I see the x squared dx right here. Okay, here it is. So I have 1/9 du equaling the x squared dx. So I'm going to be able to rewrite this problem so that I wind up having the integral, and I'm going to write it the way I like it, which is with 1 over the u, okay, sitting there. The x squared dx is really the 1/9 du, but that 1/9 is a constant, so I can just move that out of the way. And see, then I have this basic rule now that I'll follow that says that should equal that the integral of 1 over u du would have been the natural log of the absolute value of x. Oops, u should have said absolute value of u plus c. And then finally, all I've got to do is replace the u with the 3x to the third plus 7. Okay, with plus c. All right, so that's the key time when you have to use the natural log idea. Okay, and you can check it by doing the derivative, because you know the derivative of the natural log of something is 1 over that thing. So if we did the derivative, we'd get 1 over this, but then we'd have to do the chain rule, right? So that 3x to the third plus 7, when you do the derivative of that, you'd get 9x. So it's a good thing we had that 1/9 out in front here, because then it knocks that constant out. 9x squared, I should have said. That 1/9 would then knock out the 9, and you'd get what you're supposed to get. Okay, so do the check, do the derivative to double check it if you have time. All right, and then this is a case where we've got this rational function, but we can't just divide the x into everything, because it's not just an x, it's an x minus 1. So you can't just rewrite this and then use the power rule for each term. So this is the one where you use synthetic division. Okay, and with synthetic division, what goes in here is the root or the 0 of that denominator. What causes the denominator to be 0 would be 1. Okay, then you always bring down the first number. Then you multiply and write the result. And then be careful with your positives and negatives. -3 plus 1 would be -2. Multiply, write the result. Every time you go straight down, you're just adding. When you grab that number over in the left, you're multiplying. Okay. Oops, I skipped one. I went over all the way to the end and I should have gone right here. 5 and -1 would be 4. And then 1 times 4 is 4. And so I wind up with a remainder of 2. Okay. So what we're doing is we're rewriting what we have currently as almost like an improper fraction. I'm rewriting it as a mixed number. It was degree 4 originally, divided by degree 1. So this would be x to the third minus 2x squared minus 1x plus 4 plus the remainder over what you were dividing by. Okay. And then there's still the dx there at the end. And now we're ready to integrate. And when you integrate stuff that has pluses and minuses, you can integrate each term. So we'll just do that. So this would have been x to the fourth, but we got to knock the 4 out. This would have been x to the third. We already had the -2, but we need to knock the 3 out. X must have come from an x squared, but we got to knock the 2 out. 4 would have come from 4 with an x on it. We need the 4 so that there's a 4 left. And then right here is why this is part of the logarithmic differentiation. You have that x minus 1 to the first power in the denominator. You're going to need to use the natural log. So this will be -2 ln absolute value of x minus 1. And then don't forget to put that plus c on it. Okay. All right. And then that's your answer on that one. All right, now the other thing you do, we've integrated some stuff that had trig functions in it. Like we know if we see secant squared x dx and we're trying to integrate that, we know that came from tangent. Okay, because we know our derivative rules. Or if we have secant x tangent x, we know dx. We know that came from secant x. Right? Or like if we're trying to integrate cosine x, right? That had to come from sine x, and I want it just to be sine x, not negative, because the derivative of sine is positive cosine x. Okay, so those are some of the trig functions we've already been differentiating. But what if we wanted to, or integrating, I should have said, but what if we wanted to integrate not secant squared x, but just secant x or tangent x or something like that? See, if I try to integrate tangent x dx, okay, I can't think of a function off the top of my head that would give me tangent x. Okay. So what I'm going to show you is why it turns out to be the way it does. So I'm going to work the reason for show you where the formula came from. I'm going to do the same for secant, and then we'll use it on a problem. Okay, so we can justify why the formula turns out the way it does by using a trig identity. Tangent is sine over cosine. Okay, so you see how this has a denominator to the first power? That cosine x is going to be, so this I'm going to think of like this. Let me just rewrite it so you can really see it. I'm going to think about it like 1 over cosine x and then sine x dx. So do you see this right here is going to be like my u, right? So u is going to equal cosine x. So I'm going to be able to think about this as 1 over u, which when I integrate 1 over u, I'll get natural log of u. But when you do the derivative of cosine, you get negative sine x dx. I see the sine x, so I'm going to have to adjust that and replace the sine x dx is going to get replaced with negative du. So I really have negative 1 over u du. Okay? And then the 1 over u du is the natural log of the absolute value of u. The negative just gets brought down, and then I've got that plus c. Okay? And then I'm going to put my u back in, and my u was cosine x plus c. So that's why the rule on those trigonometric ones involve natural log, is because those functions are the trig functions that have denominators that are ratios of things. You'll wind up having to use natural log in the rule. Okay. All right. Now I can show you secant x as well. So if I were trying to integrate secant x, not secant squared x, just secant x. Secant squared x, I know to integrate. That would be tangent because I know my derivative rules. But if it's secant x, I'm going to do not a similar thing. I'm going to try to see if I can figure out what to do with that. All right, now this one's more like a trick. Like you'd have to know what to do to have the idea of even doing this. But it does prove why the formula turns out to be what it is. So what I could do, what makes this work, is if I multiply by secant x plus tangent x. And like I said, you wouldn't just think to do this. Like, why would you even dream of doing that? But if I want to multiply by secant x plus tangent x on top, then I need to do the same thing on the bottom. Like that fraction I just multiplied by is really 1. So I'm not really changing the problem, but it allows us to then get this to work out. Because see, on top we would have secant squared x plus secant x tangent x when I distribute that secant x all the way through. And remember, fractions work like this. Secant x would get multiplied on the numerator, and then the denominator would just stay secant x plus tangent x because of that understood 1 right there. Okay? Then what I'm going to do is I'm going to let u be the secant x plus tangent x. And when I do the derivative of secant, I get secant x tangent x. When I do the derivative of tangent x, I get secant squared x. Okay. Well, look, that's exactly what I now have. That's exactly what I now have right there. So that right there equals du. Okay. So I can rewrite the problem as 1 over u du. So I wind up getting, I want to go ahead and do it. I wind up getting the natural log of u, absolute value of u, plus c, and u is secant x plus tangent x. And then I got to remember to put that plus c on it. So that's the formula for the integral of secant x. Okay. All right, and we could do similar things to get the formulas for all the other ones, similar tricks to get the formula for all the other ones, okay? And we already know the integral for sine and cosine, so then we're just adding in what to do when you have the functions tangent, cotangent, secant, and cosecant that are defined as ratios. That's what you do about it, all right? So then you can use it. So then if you're trying to do a problem like this one that was on the integration test, it's the secant of something. So u equals 5 theta plus 7. So du would equal 5 d theta. So d theta would be 1/5 du. 1/5 du. And this is now secant u. And I'm trying to integrate that. So I'm going to bring the 1/5 out. And then I just need to use the rule. And the rule is that I would get ln, the absolute value of secant u plus tangent u. I had a 1/5 out in front, and I got to remember the plus c at the end. And then I'll go back and I'll put in that 5 theta plus 7. So this is 1/5 natural log secant 5 theta plus 7 plus the tangent of 5 theta plus 7. And then plus c. Okay, so that's the idea on those. And try to learn the properties, but like I said, I'll let you do the final, and then I'll give you a formula sheet to do the problems that you were allowed to use the formulas on the regular tests. Okay, so let me stop this and get it posted.